Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 12, 2025, about 4 days ago. This paper introduces the first end-to-end video editing system that explicitly separates a scene's hidden physical properties like albedo, normals, materials, and lighting, so it can propagate keyframe edits through an entire video in a stable, photorealistic way. The paper is titled V-RGBX, Video Editing with Accurate Controls over Intrinsic Properties. And as we dig into the method, the ability to relight and restyle videos with this kind of precise control turns out to be really exciting. Also, the authors shared a GitHub repo for V-RGBX. Right now, it mainly outlines what's coming: open-sourced pre-trained models, intrinsic conditioned video editing inference, inverse and forward rendering pipelines, plus full training code. So the implementation will be accessible there as they gradually release these components. Figure 1 illustrates what the system actually does to a video once a user edits a single keyframe. Each row shows a different kind of change, like object retexturing, material tweaks, relighting, and normal edits, which adjust surface orientation. The first column shows the original video, while the second column presents the manually edited keyframe. The third column displays intrinsic properties, such as albedo, meaning base color without lighting, or irradiance, meaning incoming light. The remaining columns show how the method propagates that intrinsic edit across the whole video while staying photorealistic and temporally consistent. Figure 2 explains how the full V-RGBX pipeline turns an input video into editable physical layers and then back into an edited video. The top left block shows the inverse renderer, which converts RGB frames into albedo, normal, material, and irradiance channels. The top right sampler chooses which intrinsic frames, including edited keyframes, will condition generation. The lower half shows the forward renderer, which mixes the intrinsic video, keyframe reference, and temporal intrinsic embeddings so that the diffusion transformer can synthesize a temporally consistent output video. Figure 3 shows how different video editing methods propagate a single intrinsic change through time, and it makes the visual advantage of V-RGBX very concrete. The top half compares solid color and texture edits, where baselines drift or gradually change unrelated objects, a problem the authors call property drifting. The bottom half compares material and normal edits, which often get mixed up in other methods, so lighting or geometry changes bleed into each other. Green arrows highlight the intended keyframe edits, while red arrows and boxes mark artifacts such as fading colors, moving highlights, or warped geometry. Across all 4 blocks, V-RGBX keeps the edit stable and confined to the correct intrinsic property throughout the video. Table 3 shows that when you run videos through the full loop, from RGB to intrinsic channels and back to RGB, this method preserves content and timing much better than the baselines. Cycle consistency here means the round trip should reconstruct the original video with minimal distortion. On both the Evermotion synthetic data and the Real Estate 10K Real videos, V-RGBX achieves higher reconstruction scores and much lower video distance, so edits stay faithful and temporally coherent. The highlighted rows emphasize that this holds across both datasets, which underscores the robustness of the intrinsic-based pipeline. So while Table 3 examined the full round trip, Table 2 focuses on how well different methods render RGB videos directly from intrinsic channels. The table compares peak signal to noise ratio, structural similarity, perceptual distance, and a metric called Fréchet video distance, which measures overall video quality and consistency, so lower is better. The overview shows that both traditional RGBX and diffusion renderer trail the new method by a wide margin. The third row reports V-RGBX without any RGB reference frame, which already gives much sharper and more stable videos. The final highlighted row shows V-RGBX with a single reference frame, delivering the best scores across all metrics and the lowest video distance, which means the cleanest and most temporally coherent output. Alright, the big takeaway is that V-RGBX turns video editing into a physically grounded problem, decomposing scenes into albedo, normals, materials, and lighting so single keyframe edits propagate cleanly through time. That unlocks stable relighting, retexturing, and future controllable video tools. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.